I'm going to go to the white screen. We can check it out that way. I'll take you through the working for it. So the probability that she has a boy is 0.536. And so the probability that she's going to have a girl is the other 0.464. Are you happy about that?
Yeah.
And the birth of sex is the two children are independent. Okay, so she has a boy, she's just as likely or unlikely to have a boy the second time, right? There's no interference with the probabilities, okay? And we're being asked to find the probability that she has one child from each sex. Great. So let's do a tree diagram. First child is a boy or a girl. Second child is a boy or a girl. This is not the only way to do it, but we're in tree diagrams, let's do it. A boy is 0.536 and a girl is 0.464. And since nothing has changed depending on what happened previously, I can use the exact same numbers for all these branches as well. Are you okay with that?
Yeah.
Okay, so what we need to go hunting for is one of each, right? Well, one of each is a boy and a girl, so it would be this one, right? It could also be a girl and a boy, which is this one. So I'm going to multiply these two together. That's 0.536 times 0.464. And that's going to tell me this one. And if I go this pathway, I end up with essentially the same two numbers, but just switched around in the order. And so the probability that she gets one of each is this one plus that one. So, like, calculate.
So you add them?
Yes.
That makes more sense.
Okay. So 0.536 times 0.464 is that ugly decimal. Can we make the assumption that's going to be the same guy? So can I just do times 2 because it's quicker? And the answer we get is that it would be 0.4974. What kind of accuracy they want? No, that's as good as you need to do it. And that's the answer they're looking for.
Okay, because I did the part where you multiplied the two of them, but I didn't realize you had to add them. That's what I was missing. Thank you.
So I'm not sure what you did after that, but you get most of this. You just didn't do the last little bit at the end.
Yeah.
No, that was easy fixing. Any other questions? Anybody else?
I have a question on number 11.
From
probability A.
Okay, that's the same one. Well, I've got this one set up, so at least I can get the question, I think. Is this one equally likely born in 7 days of the week question?
Let me look real quick. 11. It's part C was the part that I couldn't get, but that's the problem. Yeah.
Okay. What is the probability that both friends were born on the same day? Right. That's what you're being asked. Probability, both friends on the same day. Right. So the way I'm looking at that is I'm going to find the probability that both of them were born on a Friday, which was the answer to question B. And that ends up being 149. Right, so you already had that answer, I hope. Are you happy about Friday and Friday is 149? And then I say, oh, well, what does that really mean? Well, doesn't it mean that they were both Mondays, or they were both born on Tuesdays, or Wednesdays, or Thursdays, or Fridays, or Saturdays, or Sundays, right? And isn't the probability of both of you being born on the Monday also 149 for the same argument that you would use to get that one? And Tuesday would also be 149, and Wednesday would be 149, and altogether, isn't there 7 of these being added together?
Okay.
And if you add 7 of these together, you get that. And then lo and behold, you end up back at 1/7.
That's fine. Okay.
Does that make sense?
Yes, that does.
Wait, so you just add the probability of one of them, but like 7 times because there's 7 options?
Yes.
Oh, okay.
It's kind of like this, isn't there? 2 options, but they're both the same. Even if they aren't the same, don't you still add them? You find all the options and then add the options together. In this case, there are 7 options and you add them together. Here there were 2 options and you added them together. Any other questions?
I was wondering if you could go over again how to find the probability of A and B, and then the probability of A or B, just because I seem to mess that up a lot.
Okay, so
I don't have any specific questions.
that's okay.
But
We're going to do an A and B, and we're going to do an A or B. And I'm going to pick cards because they're nice and flexible. So
Yeah,
let's have A. What are we going to have here? A can be clubs, and B can be face cards. Now, if you're doing A and B, you're basically wanting to find the probability of both things. Not very mathematical, but that's what I mean. So what you need to say here is, okay, there are 52 cards. How many of those cards are both these things? So in English, that would be how many of these cards are face cards that are clubs. So if you imagine the 52 cards, how many of those 52 are club face cards?
3.
3. So that gives you your answer. Now, if you want an A or B, a little bit trickier. There are 52 cards. Clubs, there are 13. So that's the A bit, right? Added to face cards. Now there are 12 face cards. Take away what I'm going to call, well, I'll tell you what I'm going to call it. Essentially A and B. Take away the double dipping. So there are 13 clubs, there are 12 face cards, but aren't some of those clubs face cards? And there are 3 of those. So if you subtract that, that takes it away. So what you end up here with in this case is 22, 52. So an OR means A or B, right? I guess or both, right? And A and B is just the both. Now, when I say or both, remember you're taking away the both because of the double dipping, right?
Okay. I
Listen.
feel like I had a good, I don't know. I just remember doing the homework and there were questions like that and I was really confused on how to do it. But I remember knowing how to do this. So maybe I'm thinking of something differently.
I got one of them wrong on question 10 that was that way.
Okay, is this on A or B?
A.
Okay, let me go back to B then and see if we can find that guy.
Yeah, lots of people were struggling with the homework.
Yeah, I think this particular section is kind of all over the place as well, which doesn't help. I think the last section was a little bit clear cut because it was very similar each time, but A and B are all over the place. B, what question was it? 10?
Question 10, part D is where I struggled.
Okay, let's do 10.
It was with coin tosses.
Oh, no, my question 10 is to do myopia, so I'm not in the right place. A or B again?
Chapter 7, Introduction of Probability A homework.
Oh, it was A. Okay, I was in the wrong place.
I remember having difficulty with that one too. And
Oh.
the days of the week one, I did how you showed us how to do it a while ago of writing out all the different possibilities and then
Right.
doing it, and I drove myself crazy.
Well, you have to make sure that if you're going to write down all the possibilities, that you have a systematic way of doing it. Otherwise, it will drive you crazy because
Yeah.
you'll find 11 and you'll never be able to figure out who the 12th one is because you don't know what it is. Okay, so this question here, let's show it in all its glory, and that way I can maybe fill in the answers that way. What we're looking at
I
here,
got it wrong and I guessed it 5 times, so it's just gonna stay wrong.
okay, but hopefully at least can you see it now?
Yes.
Okay, so A is getting ahead on the first toss and B is getting ahead on the second toss. And A and B means getting ahead both times. And A or B is getting it anytime, right? Essentially. Okay, so what's the probability of the first one? We're just going through it, even though I know you got this bit right. It was a half, agreed?
Mhm.
And that one is a half. Agreed?
Yes.
Now, using the multiplication rule says if you want to get A and B, as long as A and B are independent, you can just multiply them together. So whatever happens with the first coin had no effect on the second. That's why we're allowed to do this. And so what you would do is you'd take a half, multiply it by another half, and the answer you'd get would be a quarter. Okay?
Yes.
Now, to get the A or B, I'm going to write it as a little formula. It's going to be the probability of the first one plus the probability of the second one, take away the double dip. And the double dip is the A and B bit.
That's what I forgot to do.
So what you do is you say a half plus a half, take away the quarter. And what you're left with is 3/4.
3/4. Right. Okay. I just kept doing the adding together.
And the adding together would have worked totally fine if they were mutually exclusive, right?
Right.
But there is a, you could get a number on one and not on the other, or a number on the second one but not in the first. But you could also get them overlapping and all sorts of. They're interacting in various ways, and so you're not really going to be able to just say, like we did in the previous two. Couldn't you just add the number of times it happened? This guy plus this guy, or these 3 events, and adding them together. Those were allowed because those events are all unconnected to each other directly, right? There's no overlap.
Right.
Can you kind of explain how the multiplication rule and the addition rules work? Like you can only use the multiplication rule if they're
Independent.
independent.
Yeah.
And then the addition.
Right. The addition rule goes something like this. There are a number of different situations, and depending on what the situation is, the addition rule, as you would call it, the OR rule, right? So here's the first one. If the 2 events, right, these 2 things, if A and B are mutually exclusive events, right? They share nothing in common. Then you can just find A or B by adding them together. If they share something in common, right? If there's an overlap of any kind, so they are not mutually exclusive. In that situation, then the A or B rule becomes the probability of A plus the probability of B, take away the double dipping, which is basically both things happening. So in our card game, that would be clubs plus face cards, take away face cards are clubs, right? That's what the formula looks like. We tend to just do a big fraction where the bottom number's 52 all the time, but that's what the formula looks like.
So it depends whether or not they're mutually exclusive. Does it matter if they're dependent or not?
For these, it has no effect, because
Right.
if you're mutually exclusive, you're going to be dependent, aren't you? I mean,
Yeah.
so,
Yeah.
so if you know one, you kind of know what the other is. So as long as you know what this is, you're fine. Now, on the other hand, the A and B thing, right? Those questions, the A and B, they're and the multiplicative rule, which is the one you were talking about. Says that if A and B are independent, right? So if we know they don't have any direct connection to each other, if you want to find A and B, then you can just multiply the two of them together. And that's called the multiplicative rule. And we sometimes do that, you know, like you throw a coin in, it's a half, you throw a different coin, it's a half. So the chances that both, you know, are heads is a quarter, that kind of story, right?
Okay.
So if they are independent, then the multiplicative rule will work. Now, if they are not independent, if they are dependent, then that rule doesn't work. You have to calculate those what are called conditional probabilities, right? So if A and B are not independent, you don't find A and B directly, you find these guys instead. The question A and B, you could do it by counting, I guess, right? You could do it other ways, but you can't do it by multiplication. So I would just say, how many red cards are face cards? And I'd put the number at the top, right? I wouldn't use a formula. I would just count how many times it happens. That would probably be the best. Or you might want to use some conditional, what's the probability of A given B? Now that's not giving you ands, but when they are dependent, that there is important. Right, because,
So,
yes.
so if they're independent, you can multiply them to find the A and B probability. But if they're dependent,
You better count.
what?
You better just count the numbers in the story.
Okay.
Right, so I'll give you an example. If I went and said to you, what's the probability that you got a heart and an ace? Well, I know there's 52 cards. Don't I know that there's only one of them is a heart and an ace?
Yeah.
I would count it, right? So if you were looking for an and story in that kind of question, don't try and use a formula, just count them. Just imagine the deck of cards and how many of them would be both heart and ace at the same time. For instance, if I said to you, what is the probability that was a heart and my favorite face cards? Wouldn't you say, okay, there's 52 cards and how many are face cards that are hearts? Right? I'd say 3 of them, right? And, you know, if I said, what's the probability that it's red? And what? Red and a king. There are 52 cards in the deck. How many of them are red kings? That's kind of how I would do these kinds of questions.
2.
So, do you see in these kind of questions, there isn't an A times B thing going on?
Yeah.
Right. Now, if I was throwing a coin 5 times in the air, and I wanted to know what's the probability that every single one of them was a head, that's a different kind of story now, right?
Yeah, those are more of the ones that I.
Right. So in those ones, the multiplicative rule works. Because don't you just multiply each one together? Because one coin being a head doesn't affect the next time you throw in the air that it's still going to be a head the next time as well, right? And when they're independent, you can use the multiplicative rule.
Okay. That makes a little more sense.
Right. So, yeah, don't think of multiplicative rules very often when it's only one card being picked from anything or one thing happening. Think of the multiplicative rule being more adapted to doing the same thing 3 or 4 times and try to find the probabilities. That's when the multiplicative rule kicks in. Okay. Even although you both use the word and.
Yeah. And then I had more of like a technical question too for
Yes.
the probability homework A, question 6, I think part A. Just the way to format that answer, I wasn't really sure, and a lot of
Uh-huh.
our classmates weren't sure either because I almost ran out of attempts.
Okay,
trying to
let
figure
me,
out how to-
yeah, that one had been driving me crazy too.
Because yeah, no, I was
Here it goes.
asked around and no one was really sure how to format it. So.
It goes like this.
It didn't like it when I put in parentheses.
Oh, it does. I've already done another student and it works.
Okay, so I'll try again.
Don't put any more parentheses around it. Just these guys here. And
Okay,
put a comma between each of them because one of them did everything except the extra commas. It is very pernickety about how it wants that.
yeah, it's very nitpicky. That's why I was
Very,
getting a headache trying to figure it out.
It gave me the same problem, but once I put the commas in, it was fine.
yeah. So are you talking about these commas and or
Have
these
to make
ones?
sure all of the commas are there.
Every single one, including the ones in the brackets and outside the brackets.
Yeah.
Yeah.
I think my other question, sorry, my other question was on that same homework, question 13.
Okay.
I just had a hard time figuring out all
A
that
has
stuff.
not been your friend. I got it.
Yeah.
Okay. So I'm looking, this one's to do with Republicans and stuff like that.
Yeah.
Great. Okay, let's look at that one and see how it goes. Here we go. There we go. In an election, 62% of the voters are Republican, 38% are not. Of the Republicans, 60% voted for candidate X, and the non-Republicans, 5% voted for X. And then you're being asked to find various probabilities based on that information. The best way for doing that question would be using a probability tree. So that's how I would tackle that question. And let's show you what it would look like.
Okay. I got thrown off a lot by the I forget what it's called. The A with the C. thing.
Okay, right, that's the complement of A. Some of these questions you can answer without the probability tree, but the ones I'm really, well, a lot of these questions you can answer without the probability tree, but if you've got the probability tree, they do everything. So that's kind of what I'm doing. So I'm going to start with the first split. And the first split is you could be a Republican or you could be not a Republican, I guess. That's how they want to phrase it. And then you could vote for candidate X or not vote for candidate X. And you could vote for candidate X or you could not vote for candidate X. And now I'm going back to story, and 62% of the voters were Republican. So that makes that 0.62, which means the other 0.38 were not Republicans. Of these Republicans, 60% voted for candidate X. So what fraction, what decimal won't vote for him? Not X. Yeah, great.
40%.
Yeah, the 40% as a decimal, you're right. Of the other, only 5% of the not Republicans voted for candidate X. So would you agree that is 0.95?
Yes.
For there, right? Now, we can now start answering some of these questions. Even if you've got this one, I'll put it in for completeness. I better put down what E is. E is you voted Republican, and B is that you voted for candidate X. Okay, now P of A is the probability that you voted Republican, and that one we were just basically told. So we're just writing it down. Now, that's called the complement of A. The complement of A means not A. Right.
Wouldn't that just be 1 minus 0.62?
Yes, and that would be in my table, my little thingy here. That would be the 0.38.
So that's the probability that they're not Republican, right?
Yes, or not whatever he is in a different story.
Yeah.
Right, now these are conditional probabilities. What's the probability of B given A, which is what's the probability that you voted for candidate X given that you're a Republican? Well, if you look up here, this is a Republican, and this guy here is the probability that you voted for X. So if you tell me
Okay.
a Republican, I'm now here, and then I just need to look which of these two is going to be the guy I'm looking for. If you're asked for B given not that guy, it becomes probability you voted for X. I guess just put the whole thing in. You voted for candidate X given that you're not a Republican. So if you go down here, not a Republican, can you see that that is 0.05? And that's where that came from.
Yeah, I didn't think to make a tree, but it's a lot more helpful.
I think when the questions get, you know, those ones where 70% of this and 10% of that, and then later on 40% of the ones who said Jez did this, and you know, like the airline ones, those, and that information is best described in a tree format. And now that tree can then be turned into a table, and sometimes the table that you make is very helpful as well for calculating things. So the table I would be doing if I had more complicated questions might look something like this. Republican, not Republican, voted for X and not voted for X, right? And inside each one of these, I'd be putting what these guys here are, right? These four answers. So for instance, this last one, this bottom one, would be not Republican and then didn't vote for X. So 0.38 times 0.95, and the answer I get here is 0.361. So in my table, not Republican, not voted for X, 0.361 would go there. And the reason why that's helpful is, can't you then add up columns and get percentage who are not Republicans, or add up percentage of people who voted for X, or anything else that you would want to get?
Yeah. I think the ones that I was still confused on is finding the probability of the complement of A and B, and
Okay.
then finding
Right, let's find this one then.
Yeah.
What's the probability A complement and B? And I'm just going to turn them into more English. A complement means you're not a Republican, and B is you voted for candidate X.
Okay, so 0.95.
Well, not just that. That would be a given. This is an and. So if you look at my story here, I can get it from here. If you're not a Republican, you're going this way. And if you don't vote for X, you go this way. And you see that number that I just, by sheer coincidence, actually calculated? It's 0.361. So when you are given an and story,
Wait, did
and
you
it comes
add them?
from, say again?
Did you add them together?
No, I multiplied them.
Okay.
When you do a tree diagram, the ends of the branches, right, there's 4 of them. You get these guys by multiplying the 2 pathways that led to it. So if you look at this, there's 4 different end destinations. Each one of those would be found by multiplying the pathway that led to it.
Okay.
And so it's back to that and being a multiplication. And but you see in this case, it's a multiplication of 2 guys that are already known, right?
Okay. That makes a lot more sense using the tree and stuff. Thank you.
Yeah. I would never think of doing any of these questions, this type of question, without a tree, just because of the complexity of the way they give you the information. It's easy to keep track of. I would also probably build a little table, because sometimes if you build a table, oh, you say, oh, you just want this number here or that number there. You can kind of see which one the story is asking for. Have we any more questions?
This has been really helpful.
Then I am going to, with your permission, leave this on as part of the lesson, And if you get someone who says, I'm really stuck, you can say, oh, at the end of Friday's lesson, he had some stuff there that I think might be of help.
But yeah, this has been very helpful.
Okay. Any more before you go?
I think I had one more. Oh yeah, on the part B, question
Okay.
4, it was just a small question.
Right.
Whether it's the interpretation of probability or it's asking if it's relative frequency or personal. And I was just confused because a couple of them, I'm not sure whether it should be defined personal or not. Like on part A, I don't know what Krantz is, but the probability that a random selected American will be injured by lightning, because I don't know if that means that they have personal background or if they use like.
Right, let's go with this one. The thing Krantz, if you hit the little plus symbol, actually gives you a page number and a reference that it was collected in 1992. So to me, that means this is data that was collected by someone, physical data. So
Okay.
not your pal next door who just says there's an 82% chance that, you know, I'm going to get drunk tonight. That would be a personal probability, right?
Yeah. No, I remember the difference between them. I just wasn't sure if that was like, okay, is that your own knowledge or is that from data?
Yeah, if you're thinking Krantz is just a guy's name, then it would be
Yeah, no,
personal knowledge.
that's why I was confused.
Yeah, Krantz, I'm assuming, might be a person's name, but he also collected data the real way, right? He collected
Yeah.
a sample and
And
whatever.
then on the others, it's according to my neighbor, that one's personal. According to
Yeah.
the nursery where my neighbor purchased her tomato plants, if a plant is properly cared for, the probability that it'll produce tomatoes is blah, blah, blah.
Yeah.
Would
That's
that
a
be-
relative frequency.
Okay,
But assuming that the nursery guy has actually sold lots of tomatoes and he's collected, you know, some
Yeah.
data on which, you know, how many of them tend to make it, right? Because people will probably bring them back and say that thing died on me, you know, and he'll maybe, you know, whatever, collect information. D, which is the husband outlived the wife one, that one there has a little plus beside it, and the plus is from Krantz. I think Krantz must be, I don't know it because I'm not American, and I certainly wasn't here in 1992. I think he might be a person or a book that's published by him that collected data on just general knowledge about America. So if you got a hold of that book, it might tell you that, you know, 2% of people are likely to die in freak car accidents or something, right? He just collects data on all sorts of things because he
Okay.
collected data on people being hit by lightning. So I'm pretty sure it's not just typical numbers that person's collected. So
yeah, no, I figured. Thank you so much. This has been really helpful.
Okay.
Hopefully I'm not forgetting anything.
well, you know, shoot me an email if something comes up.
All right, will do. Thank you so
Right.
much. Have a lovely rest of your day.
Okay, can I assume that it's okay for me to put this conversation with the questions online?
Oh yeah, that's fine.
Okay, anybody else got questions?
I was wondering if you could go over question 4 on evaluating probabilities.
Who is talking? Because I can't see you.
Natasha.
Okay, so what number again?
Question 4.
On section?
Evaluating probabilities. It was the one you went over today.
Oh, the today's stuff. Sure.
Yeah.
Let's find out what that one looks like. Are you looking at the questions or the whiteboard right now? What are you doing? What can you see, I should say?
I'm looking at the question on my other computer.
We can
Okay.
only see you right now.
Yeah, on Zoom.
Oh, you just seen me. Okay, so let me zoom over and share that question on the screen. And let's see what we got here. This is to do with the left-handed, right-handed thing, isn't it?
Mm-hmm.
And it says, consider randomly drawing 2 students without replacement from a class of 50, in which 2 are left-handed. Okay, so they keep changing the numbers, right? So the one I did won't be the numbers that you'll do, right? But anyway, it's still 50 students, 2 are left-handed. And here is the tree diagram. And we're going to create this tree diagram, and each of these ABs is going to go in here somewhere, right?
Okay.
Okay, so I'm going to now leave that and look at how I would create the tree diagram. I'll try and create it the same way that they have, so my A's and B's all match up. So They use a phrase here that's quite important to these questions, and it's called without replacement. So essentially, we have, I'll call them left-handed. I know they're calling them not left-handed, but I'm just going to call them right-handed. And then the second person that you pick is left-handed or not left-handed, or left-handed or not left-handed. Okay, so I'll put little bubbles around these guys. And what do we have here? We have 50 people. And out of this particular group, 2 are left-handed, so that must mean the other 48 are right-handed. So that's really all I've got to work with. So first person, chances are that they are left-handed is 2 out of 50. And I'm not going to simplify it, I'm just going to leave it as 2 out of 50. What's the chances then that they're right-handed, the first person you pick?
48 out of 50.
Yeah, and we're using the trick that these 2 always add up to 1. And when it's fractions, I just say, look, the top 2 add up to 50. That's an easy way of remembering it, right? Now, first person's picked. That's going to change now. What without replacement means there's now only 49 people left because the first person is already chosen and that person right now is left-handed. Now that means there's only 49 to pick from. And since that person was left-handed, doesn't that mean there's only one of them left who's left-handed, at least in this story? On the other hand, there's 48 out of 49 right-handed. Are you happy about how this split happened?
Yes.
Right. Now, if the first person was right-handed, the next choice, there's only 49 to choose from, but at least 2 of them are left-handed, and the other 47 out of 49 are right-handed. Then what you're going to do is you're going to get the final probabilities, which is what these 4 things here are like. And you multiply them together. So you go 2/50ths times 1/49th, and then you let the calculator do the hard work. So put a roll bracket around it. 2/50ths times 1/49th. Horrible decimal. Oh, that's maybe not going to make it. We'll see. I didn't make it. Okay, then I'll have to do it the old-fashioned way. 2 times 1 is 2, and 50 times 49 is 2/2500. And if I divide the top and bottom by 2, I get 1/225. So I got my answer there. And they want their answer as fractions, so I had to pick that. Okay, let's do the other one. It's 2/50ths. And this one. So 2/50ths times 48 49s. I know the bottom's going to be 250. I know the top's going to be 96. If I divide it, God, maybe I could get away with that at least. 96 divided by 2450. Maybe make it. Oh, good. At least it handled that one. It's 48 out of 1225. Right. The next one is going to be these 2, and that's going to be 48 out of 50 times 2 out of 49, and that ends up being that guy. And then the last one is these 2. So it's going to be 48 out of 50 times 47 out of 49. I know the 2 bottom numbers. I don't know what 48 times 47 is, but 2256 is what I have. Then I'll try and see if I can make the calculator simplify it down. And it simplified it down to that. Now, in the homework, the picture that I've drawn, this is called A, this is called B, This is called C. This one here is called D. This one here is called E. This one is called H. This answer up here is called K. This answer here is called M. This one's called N. And this last one's called W. So you're going to have a whole load of letters that look like this. A equals in a box. And B equals in a box. And the last one's going to be W equals in a box. And you essentially type in the fraction. A is 2/50, which I've now decided should be 1/25. And this guy here should be 24/25 if you simplify it. And this last one is 1128 out of 12/25. And that's essentially how you would do that question. Are we good?
Yes, so on my question specifically, it says that 4 are left-handed out of 25. I just put 4 over 50 on the first one.
Well, in your story, there were 25 people
Yeah,
and 4 of them were left-handed.
yes.
So that would mean your split would be quite different numbers from me. So for instance, that first branch, right, the left-handed, right-handed branch, you have 4 out of 25 and 21 out of 25. You see, you're going to use these numbers. Now, when you do the second branch, the left-handed, right-handed branch, these two. Okay, if the first person is left-handed, there's only 24 people left, right? One of these is being used up without replacement. So that means there's only 3 of them left. 3 out of 24 left-handed people left. And the other 21 must be right-handed. If the first person was right-handed, there's 24 people left again. Out of the 24 people that's left, since it was a right-handed person that was used up, there's still 4 left-handed to pick from. And there's only 20 right-handed to pick from. So these are the guys you're going to multiply together to get the last 4. It's the same process, but with different fractions.
Okay, thank you. It said that the probability of selecting 2 left-handed people is 1 out of 50, and that just like kind of tripped me up.
It says what?
That the probability of selecting 2 left-handed students is 1 out of 50.
Okay, let's find out what that would look like. 2 left-handed students would be 4 out of 25 times 3 out of 24. And if I go to my calculator, let's find out what that looks like. A bracket, 4 out of 25 multiplied by 3 out of 24, and make that a fraction. And there's that 150 that they told you about.
Okay, thank you. That makes
Do you know?
it
Yeah, I think it might have been better if they hadn't told you that.
easier. Yeah,
I just let you get on with building the tree regardless.
yeah. Thank you.
You are welcome. Anything else? Barbara, if you thought of one, are we good?
Well, I'm listening and it's helping me quite a bit. So
Okay, that's good
Yeah.
with me.
I'm just hanging out.
If there's any other questions, I'm good. If we're not, I'm good too. Any more before I go?
Thank you.
You are welcome. Bye-bye, guys, then.
Thank you.
Remember, you can always shoot me an email because sometimes you don't know until you see the question, right?
Right.
So I might get emails between now and then.
Perfect. Thanks so much.
Okay, off we go then.